This is, in fact, one of the core differences between hard science and soft science. Hard science has a tendency to be notably more objective, and soft science has a tendency to be notably more subjective. Untranslatable Metaphor had this question about mathematics being, whether it's hard science or soft science or something else. And I think it's a really good question, especially because it's maybe not as straightforward as it may appear to be. And so I went to Perplexity just to keep our AI bias from stagnating. And I asked it to explain some stuff to me. So it's going to explain this, and we're going to take a look. First, I asked it to explain the difference between hard science and soft science. And then I ask it to tell me what it thinks mathematics is. And this is related to this notion of if mathematics is not a hard science and computer science is based off of mathematics principally, then how is computer science a hard science, right? Kind of makes sense. So the question is mathematics hard science? Okay, so to start, we're asking it to explain the difference between hard science and soft science, and we're going to get right into it. The terms hard science and soft science distinguish scientific disciplines based on methodological rigor, precision, and the objectivity of their methods and findings. Okay. The key words to focus in on here, I think, are the rigor, the precision, and objectivity. So rigor, just to be clear, because this is one of those cases where words are going to be super important. Rigor is essentially this notion of we're going to look at things in a potentially exhaustive or near exhaustive way. This is the rigor part. We're just going to keep deep diving until we can really understand something. The precision is the part where we want to make sure that we are as close to perfectly correct as we can be. And there are cases where we can't be perfectly correct because we don't understand all the variables, or we don't have the other advances in other areas of science to properly represent things. So you can't always get perfect precision. In many cases, it's more of a nines problem. But the goal is to try to get things as precise as possible so we understand like what we're talking about. This is super important if you want to have things be foundational for other things. So if you want to build elements that can be the foundation for other elements, the more precise and objective they are, the more likely you'll be able to build on top of them. The more imprecise and subjective they are, the more likely you can't like build a castle on top of them because it's like quicksand, right? And in particular, the last one here with objectivity, this is the idea essentially that what you're saying is essentially it stands regardless of the viewer. So if I view it, it stands. If Taylor views it, it stands. If 7.8 billion other people view it, it stands. This is, in fact, one of the core differences between hard science and soft science. Hard science has a tendency to be notably more objective, and soft science has a tendency to be notably more subjective. Now, it's, again, important to understand that hard science is not necessarily 100% objective, and soft science is not guaranteed to be 100% subjective. These are shades of gray, right? Anyway, let's continue now. So hard science, subject studies, focuses on the natural world, physics, chemistry, biology, astronomy, geology. Now, one thing that's really important to think about right here is in the hard sciences, there's this point about the natural world. This is also called the natural sciences. Now, hard science and natural science are not exactly the same. Natural, and this is where I think untranslatable metaphor was getting a little hung up, is natural science are the sciences that exist in the natural world. And to my understanding, for the most part, untranslatable metaphor is correct that computer science is not a natural science because computers are a human constructed device, or there's this other word that they use in these patents that's like slipping my mind right now, but it is essentially synthetic. And because it's synthetic, it's not something that you find in the natural world. That part is uh, pretty true-ish. Now, the reason why I say that this is like only pretty true-ish is that the components of computers are actually things that, for the most part, exist in the natural world. So one of the primary components for hardware, especially computing devices, is silicon. And so silicon is a semiconductor, and this is super important for the electrical aspect of the circuitry that underlies all of our physical embodiments of computers. And silicon is sand. It's just sand. I mean, it's like refined sand and, constructed in a way that's very precise, but it's sand. And sand is occurring in the natural world. So same thing with electricity. Electricity is also occurring in the natural world. You don't believe me? Just go stand outside when there's a thunderstorm and you'll find out really fast that electricity is just happening on its own. So while computer science is not a natural science, for sure, computers are synthetic. We created them. They do have basis in the natural world through like 1 or 2 degrees of separation. Now, I want to be super clear. I'm not saying that computer science is a natural science. I don't believe that it is. But you can see now how it's not as easy as saying like it is or it isn't, especially when you have the core components of computing devices that are principally from the natural world. All right, continuing. The methods utilizes controlled experiments and testable predictions. Yes. Relies heavily on quantifiable data, mathematical frameworks, and empirical validation. Yes. And this part is super important. It's the quantifiable aspect, that we're talking about things that we can think about in quantities, and that when we do our analysis, it's the large volume of data that helps us understand if we're correct or not. This is like a very fundamentally different property than soft science, because soft science will often be more qualitative. And therein lies one of the core differences. So you have with hard science, you're going to have things that are far more objective, and soft science is going to be more subjective. And then on top of that, you tend to have things that are more quantity based in hard science, and things that are more quality based in soft science. Now, it's not to say that you can't have quantity types analyses in soft science. You can. Like, so when they do these surveys of people, asking them various things, like for sociological types of examinations, those surveys, those quantities definitely do exist. But you will often find that the quantities won't necessarily be of the same quantities that you would see in the hard science. And part of the reason for that is being able to replicate that much data and that many experiments with things that are principally not objective. In many cases, things that are like animals or humans or whatever, it's far harder to run those experiments. Whereas we can run a whole bunch of deep analyses on computing devices with AI or whatever in a tight for loop from now until you know eternity and get a plethora of data. And we don't have to worry about things like, are people getting hurt in it? Are we having ethical treatment to animals? All this stuff. Where in the soft science, they tend to have to care about these things. Okay. Yes, and then high emphasis on reproducibility and objectivity. Yeah, as we discussed before, this is one of the most important things about hard science is the deterministic aspect of it. So reproducibility is in like one of the simplest forms, it is a byproduct of determinism. Now, you can have non-deterministic systems that also have reproducibility qualities, but you generally want to control some of the non-determinism so they become reproducible, or you have a way to reason about the reproducibility in a non-deterministic sense. So, for example, if you're doing program analysis for a multi-threaded program that is non-deterministic by nature, that would lead you to believe that you can't really get the reproducibility. Well, you can, ish. And the way that you do that is you can control the threads of execution, so you can stall certain things out, and then you can force reproducibility to occur, so things will fall into this hard science category. Now, that being said, when you do those types of things, you are now interfering with their general flow of execution. And so what you now have produced is maybe not the actual real behavior of the system. And you've basically gone down the path of the probe effect. So you may need to find another way to try to get reproducibility. The other part that is super, super critical is the objectivity. This is like, in my mind, probably one of the most important aspects. Yeah, in some sense, I think they really nailed it. It's the reproducibility and objectivity that are core for hard science. And when you think about it like this often is the clue for you to know if something is hard science or soft science. If you think about a thing in your head and you think, oh, this is highly reproducible and it's highly objective, it's probably hard science. And if you think about something in your head that doesn't have those, either it's not reproducible or it's not objective, you probably are not dealing in the space of hard science. So with these two things, we can almost immediately conclude that mathematics will probably be a hard science based on this definition, because mathematics in general is highly reproducible. There are some cases that aren't perfectly reproducible, but the majority of mathematics is, and that also is critical because keep in mind, mathematics is the foundation of a lot of stuff. And as we were discussing before, you really want things to be deterministic as foundational elements of your scientific principles. If it is not deterministic, or it's not sort of like an objective truth, you're building like a house of cards where the smallest amount of wind is going to blow this over. All right. Outcomes for this finds precise, often universal laws and principles. Yes. And notice too that the language here is important. It tends to find, I would probably say tends to find precise. And then notice they say often universal. So it's often universal, but it's not always universal. There are cases where things are contextually correct, and they change subtly based on the context in which you are analyzing them. A good example of that is the speed at which, or the force of gravity, I think, for planet Earth, and like the way that we calculate terminal velocity, and it's something like 9.8 meters per second squared, I think, as we saw from one of the prior things. The reason why I mention this in terms of often universal is that's actually not a constant. This changes based on how close you are to the center of the celestial body, which is essentially the field of gravity, or how far away you are. Like if you get far enough away from the center of gravity from the Earth, it actually has no gravitational pull. And so there's not 9.8 meters squared, meters per second squared, anything. It's just zero, right? And so why is that relevant? This is what we mean about it's being universal, but often that we have essentially an equation, and we'll sometimes just use constants and say, oh, it's just this constant. Well, actually, it's more the equation. And so the constant is like our shorthand way of saying, oh, it's just this number. Just use this number. But if you want to get actually precise, what you need to do is you need to recalculate that number based on the context of where you are, what your distance is from the center of the celestial body that has the gravitational field, or something like that, right? Again, I don't have a PhD in physics, so what do I know? But as I recall, it's something like this. And this is why it's often universal, but it's not guaranteed to be universal. Okay. Results are typically more predictable and consistent. Yes. Progress often progresses rapidly due to a clearer consensus and easier replication of results. Yes. And this is one of the reasons why stochastic AI systems are likely going to just be a flash in the pan. I mean, at least as the basis of science. I think that there'll be fun little like TikTok toys for various things. But if you just think about it logically, how can you build stuff on top of it to expand its range of capabilities when the basis of the system is shifting underneath you? Right? It's like building a house on top of sand, is that you could do it, but the house is going to sink because the sand is not solid. And so similarly, if you have a foundation model that is of the language variety and it's stochastic, then how do you build other pieces on top of that that are going to rely on its controlled deterministic behavior when it's not deterministic? It's pretty hard to do that. Now, it's not to say that stochastic things don't have value, but generally speaking, when we're talking about the advancement of science, hard science is going to give us the building blocks that we can rely on so we can keep leveling up, right? It should be no surprise that the stuff that we're building for like rockets and computers and some of the most advanced technology, this is all based off of essentially a stack of science that is almost all hard science. Almost all of it is hard science because it has that clear consensus and easy replication of results. It's going to give you the same stuff. So then when there's a mistake, you just fix the bug and then the bug goes away. But as we saw in many of the prior discussions with stochastic AI, it's not going to give you these things that are reliable. And so what do? Notice too that these systems that we're talking about, the language models, these are generally considered hard science. And that's why we say often progresses rapidly due to this. But there are cases where it is not actually going to give you these fully predictable, right? So again, the language here is super important. Results are typically more predictable and consistent, typically, but not always. Thus, language models. Yeah, often. Yeah, T. Exactly. Yeah, I love it. All right. And then examples are physics, chemistry, biology, astronomy. Now, let's look at soft science. Subject studies focus more on human behavior, societies, and complex systems, psychology, sociology, and anthropology, and economics. These are all, notice, the common theme of all of these is humans. Psychology, humans. Sociology, humans. Anthropology, humans. Economics, humans. Societies. Yeah, I guess that's sort of in this. This is humans. And the big thing here is that humans are not objective. We are subjective creatures that do just strange and wonderful things. And I think it's part of what makes us so interesting, but it also makes us really not the best subjects for the foundations of truth, because even the best intentioned humans can get stuff wrong. Like, I'm trying my best to only say things that are like factually correct on GTT, but I don't always get it right. I get some stuff wrong. Whereas if we had a computer doing this, the computer would probably, well, almost definitively would have a larger degree of accuracy than I would. So in the soft science space, what we're really talking about generally, I mean, there are probably corner cases here. Again, I'm not an expert. I'm more of an expert in hard science. I'm less of an expert in soft science. Although my ex-wife, who is one of the premier soft scientists, experts alive today, at least in sociology, I was married to her for like 13 years, and she taught me all kinds of stuff about this. So I probably know a little bit more than maybe the average hard scientist person, but this is still completely out of my realm of like deep understanding. Yeah, so T is just saying he's liking the precision of the language we're calling out, especially the fact that so many things aren't either or, that it's important to acknowledge the gradients of life. Yeah, absolutely. And it is very strange because even in things that we feel are either or, black and white, instead they end up being gradients of truth. And an example of that, or at least one example that I think I'm aware of, and all the physicists in the crowd can let me know, it's my understanding that we sort of have two different views on physics. There's Newtonian physics and there's quantum physics. And Newtonian physics work really well until you get to the really small. And once you get to the really small, my understanding is that Newtonian physics kind of breaks down, and then we switch to quantum physics. At least that's my lay understanding of this. How is that relevant to what Taylor's saying? This is a really good example of how you can't just say, oh, yeah, physics is just all Newtonian physics, and that just covers everything. It's actually more like, well, you use Newtonian physics up until this point-ish, and then you kind of switch to this quantum thing, which tends to be more accurate when you get into the small space. Where is the deciding point? I don't know. I have no idea. We'd have to ask like a physicist that's maybe an expert in both. But the point is that even in hard science, where things are like, this is mostly true for this thing, then you get into this certain context, and then suddenly, contextually, it doesn't make sense anymore. Really interesting subtleties in science. And also going back to the point that there is this general belief that science, especially hard science, is perfect. The truth is, not exactly. Like a lot of this is experimentation. I would like to believe that one of the things that we're hopeful for is that the mathematics and the logic of these things are Taylor and his fun puns. Okay, I got totally distracted by Taylor's comment. I can't recall what I was saying, but I think the higher order bit is that hard science is not always 100%, and that is predicated by a few different things. One, the thing that we're looking at can be correct contextually. So it's like right in this space it works. That's the Newtonian versus the quantum physics. But then it also could be that it's correct, except we have limited understanding of this field. And so it's not totally correct because there are hidden variables that we don't understand that we need to advance the science in. And that's part of the reason why we have the scientific method, is that we can explore this. We can be like, oh, your theory, Bob, it worked great in all these cases. But then I went to the moon and then it didn't work anymore. Okay, so what is happening on the moon that makes it kind of fall apart? And these are, I think, important questions. Okay, so soft science, dealing with all this human stuff, methods often use qualitative research. Okay, cool. Like we were discussing before, go back to the methods over here. This is often quantifiable data, right? Because quantity. And now when we get into soft science, it tends to be qualitative research because it's quality. And this kind of makes sense when you think about humans as subjective creatures, is that if we were all the same, it might make sense to look at all of us humans in a quantitative way. But because we do things that are somewhat unpredictable, even amongst ourselves, it's more of a qualitative, like what seems to make more sense here is a qualitative analysis. And for those of you that, just look at the first 5 letters. Is the quant is quantity and the qual is quality. And you can do both, right? But generally speaking, if you're in the soft science, the qualitative tends to be the more common way that you do things, like through these interviews, surveys, case studies, all that stuff. And again, it's not to say that you can't do quantitative analyses. It's just that this tends to be like better predictor of things because it allows you the subjectivity that exists principally in humans. Okay. It deals with inherent variability and complexity in subjects, making controlled experiments difficult. Yes. Again, that's why doing it at a quantity level can be challenging. Less ability to isolate variables or produce strict causality. Yes. So the idea here is even if you run these experiments and you get an outcome, then you could run the same experiments again with 10 different people and get a totally different outcome. So it's very complicated. In fact, my ex-wife and I would talk about this all the time, and she would say she thought hard science was much more difficult than soft science, and I would tell her I actually think it's exactly the opposite. I think soft science is significantly more difficult because there's so much nuance, and it's really hard to say anything somewhat definitive. Whereas going into like mathematics and computer science, we can say int x equals 7. And that's just an integer with the variable name x, and it's going to equal 7. It's going to do that every time. And if it doesn't do that, well, then something is broken. It's not our system. Like that's the beauty of hard science, is you can just absolutely correctly know. It doesn't mean that there's only one solution. It just means that you generally can verify correctness of a solution or properties of a solution in a easy to repeat way, where it's not the same with soft science. Okay, now let's continue. Outcomes generates insights about trends, patterns, and influences rather than universal laws. Yes. Results can be less predictable and harder to replicate exactly. Yes, we talked about this. Progress usually slower due to ongoing debates and variability in the data. Yes, this is my argument about why this is much more difficult. Is like humans are stochastic creatures. And when you have stochastic creatures, it's very hard to make these kind of like universal claims because they're not universal. That they're based on sort of what we're seeing right now. And then that could change tomorrow. Thus, part of the reason why Mentor And Merle's AI is built, it's all largely machine learning, just like language models are, and graph neural networks, or generative adversarial networks, or whatever, convolutional neural networks. You pick it, whatever. Still machine learned. The difference is that the Merle stuff is nearly perfectly deterministic. There is some aspects that are non-deterministic, but a lot of that relates to temporal properties, like the time that it would take for an answer. Like that, you may have some non-determinism there. It may take a second, it may take 1.5 seconds, but generally speaking, the outcomes will be very similar. With the stochastic systems, same with soft science, you don't have the same guarantees about the outcomes, because they are stochastic or they are subjective. And then it's very hard to add stuff to this because you don't know which way the wind is going to blow on the lower levels. This is part of the reason why I argue that you can't staple reasoning on to a stochastic system after the stochastic system is already in place. It doesn't work like this. You need you need the deterministic system to be underneath the stochastic piece. So then the stochastic system can be validated by the thing that is deterministic, that thing that's objective, and it rejects things that just aren't correct. If you have the system, like you have the house built already on sand, and then you attach like an anchor to the side of the house, yeah, the anchor is going to stay in place, but the house is still going to sink into the sand, right? So hopefully this analogy makes sense. Like, for some reason, a lot of people seem to struggle with this, and it's not. I don't think it's that hard of a concept. I feel like maybe part of it is people really, really, really want language models to be the future of everything. And I'm a scientist. Science doesn't have a panacea, and so the idea that you'd have a single advancement in science that would solve everything is just. It's nonsensical to me. It's actually antithetical to the whole field of science. Like just the general domain of scientific advances would scoff at this and say, yeah, it doesn't work like that. It's building this Lego blocks, right? So I think that that's possibly one piece. And I think the other piece is that people are excited about this, which is great, but then they seem to be maybe turning an intentional blind eye to the weaknesses, because it may reduce the potential valuation of companies or the promise or whatever. And like, I get it. For like the VCs or the founders that they have big plans of making ridiculous amounts of money, and then me throwing a monkey wrench into their system, basically saying that actually this is just a house of cards. It's not going to work like this. Yeah, it's probably going to be a very hard pill. I think of it as like the flat earthers. Right. I mean, I hate to draw such a harsh analogy, but it's sort of like that, is that the earth is not flat. And there's many scientific reasons why the earth actually cannot be flat based on what we understand about the universe. It just, the physics of it don't make sense for the way that celestial bodies move in galaxies and things, in star systems. Flat planets don't make sense, right? They would erode away because of like essentially the influences or the factors, the external elements that are going to chip away at this. Like, this is why they're spheres, right? They're like these perfect spheres because they've been molded into this object that has the same type of even resistance on all aspects. So there is no it has equilibrium, whereas a flat object does not have the equilibrium, right? As you flip the coin, it's going to bump like the top part of the coin every time, and eventually what will happen is it'll erode away the top part and bottom part, and it'll keep doing that over and over and over again. And then what are you left with? A perfect sphere. That's essentially like the higher order bit, at least my understanding of why essentially planets are spheres, is that they're going to chip away and make them that perfect. I mean, it's probably not exactly that, but like approximately this. Similar thing is going on with language models, is that they lack some of these fundamental properties that you need for them to be foundational to science. And if you just ask any, I think, unbiased scientist that understands machine learning well, I think we're all in agreement if we're being honest. So this is not to say in any way that language models aren't super valuable and can't be used in a number of different places. I absolutely think that they can. But if you think that they will be like the foundation of science like mathematics is, I think that's very confused. And it doesn't stand up to even the tiniest amount of scrutiny, right? Like we already can see that they can't do this because we'll ask them a question like, what's 1 + 7? And it'll be like 8 most of the time, except when it's 9 or some other number. And that's not going to cut it in cases where you need like highly reliable precision. All right. So now in summary, these are aspects that they're considering: hard science or soft science. So primary focus, natural world, physical phenomena. For soft science, human behavior. Again, this human part is really key because humans are strange creatures. And not just humans, I think animals. So mostly any kind of intelligent life, I think, can be strange and do unpredictable things that would be in this space. Okay, experimental control, high controlled, replicable experiments. Soft science, often low, complex variables, less replicability. Yes. Data type, it's more quantitative, numerical, and objective. Right. So quantitative, numerical, and objective. And then this is more qualitative. It has some quantitative properties, and it's highly subjective. Highly subjective. And by subjectivity, what we also are saying is like a way to think about this. It's not exactly the same thing. So subjectivity is saying that it's sort of how I view the world. It's the subject's perspective rather than free of a subject and sort of the view that the whole world is going to take. It has a similar type of correlation with the objectivity is similar in nature to determinism, and subjectivity is similar in nature to stochasticity. They're not exactly the same concepts, but there's a lot of parallels. And so, in short, for hard science to give you objectivity, you often need determinism. There are corner cases, but a lot of the time you need determinism. If you do not have determinism, then it's very hard to have this be the basis of hard science. And likewise, for soft science, it tends to be subjective, which lends itself to stochasticity, because subjectivity is like you don't know. Could be someone's favorite painting, could be the thing that they find the least favorite of all the art they've ever seen. It's very subjective. It's very stochastic in its randomness. Again, just to be clear, I'm not trying to say that these words are exactly the same, but I'm trying to help draw parallels so people can think about this in at least seeing how these create natural divides between the way we reason about these different types of science. Okay, use of mathematics, extensive. Yes. Almost all hard science has its foundations in mathematics. In fact, I don't know of a single discipline in hard science that isn't largely influenced by mathematics. And keep in mind, what I mean by mathematics is not just numbers, it's also logic. Because I think that first order logic is basically the basis of mathematics. It's like before we had numbers, we had first order logic. because we had things that were anded and ored together, and then from those things we could make logical conclusions, and then from there then we got numbers that then can represent quantities to then extend our logical reasoning. uh, T's got a comment here. It's interesting how you bound data collection in soft science versus hard science problems. Yeah. Yeah, and it's very it's really challenging, I think, in the soft sciences, like just the data collection, because there's so much variability that you basically can run one experiment on Tuesday and run exactly the same experiment on Wednesday and get totally different results. And in hard science, you could do that, but it's far less common, at least in my experience. Okay, predictability, high. Yes. Notice they're not saying that it's guaranteed, but it tends to be high. And as we were talking about language models, because they fall into the space of essentially statistics and probability and mathematics, they fall in this space. So most of the things in hard science are predictable, but notice it's not saying that all of them are. And this would be a case where the predictability of the language models violates this highness. And also that there sometimes can be universal laws that are possible. These are basically like the law of gravity kind of thing. Okay. And the word law here, just to be clear, it's quite strange, at least based on my understanding of this, is the word law here, it doesn't actually mean universal. It means that in all of the experiments that we've run so far, that this law has held. And usually there's like a timestamp on it, like after a century or something, that there's no counterexamples. It gets bumped up to a law, but it doesn't mean that a counterexample doesn't exist, because in many of these complex systems, you can't actually prove that a counterexample doesn't exist. The best you can show is that a counterexample hasn't yet been found. Thus the nines problem. Now, there are cases where I think we have some universal laws. And like, for example, I want to say that with the exception of the number 2, all prime numbers are odd. I think that that is something you could say as a universal law, I believe. And I think that you can actually prove that. Yeah, I'm pretty sure you can prove that. So there are cases where you can get universal laws where it says this is just going to be a truth for the universe. And it's rare, but that can be really helpful. You, generally speaking, when you find things that can be considered universal laws, those make great things for the foundation of science that you'll add on to extend that thing. Okay. And then soft science predictability, it's lower. Context dependent trends and theories. Consensus among experts. For hard science, it tends to be higher, clear answers. For soft science, it tends to be lower, more ongoing debates. And then as far as examples, we heard the examples before. All right. Additional notes. Some disciplines blur the boundaries, like fields of psychology and economics, employ both hard and soft science methods. Yeah, I was going to say economics is actually a really curious one, because economics has foundations in mathematics, but it also has foundations in societies and groups of people. And so it literally is kind of like straddling both simultaneously. Okay. The distinction is debated. Many argue that both apply scientific methods, but deal with different complexities and limitations. Yeah, sure. We can debate this till the end of time, but I think it can be helpful to understand at the highest level why the differences exist and how thinking about them as two different spaces can be helpful. Because when you're working in the hard science space, you generally are looking for things that are objective and repeatable. And if you can't get that, you may want to check yourself and say, why am I not getting objectivity and repeatability here? That's maybe not super great. And similarly, in soft sciences, you can expect that it'll be more subjective and more qualitative, more stochastic. And so, if you're not seeing that in the soft sciences, you might also be asking yourself, why are the answers so predictable here? Why am I missing something? All right. Criticism: the division can unfairly marginalize soft disciplines despite their rigorous research and societal relevance. I mean, I don't think so. I think that soft science is hugely important, and like we've discussed, I think it can often be considered more difficult. Many modern scholars suggest evaluating science by quality of method rather than by hard and soft label. Possibly. I'd have to think about this some more. I don't totally love the separation, but I think it can be useful to help understand when we're dealing with things that are more objective in nature versus when we're dealing with things that can be more subjective in nature. All right. And then we'll continue. Now to the question that Untranslatable Metaphor had is mathematics hard science or soft science, right? This gets at it. Okay. Given all of that background, so now we have sort of a deeper understanding of hard science and soft science. By the way, whenever you're trying to, like, at least for me, whenever you're trying to deeply think about something and trying to understand, like, is mathematics hard science or soft science? The first thing that I do is what we just did. Before I try to answer this question, I try to make sure I deeply understand what it is I'm talking about. So I'm going to try to make an argument that mathematics is hard science. And in order to do that, we first need to have really a well-formed understanding of what hard science and soft science are. Because unless we agree on what these definitions are, or approximately agree, then how can we possibly agree what mathematics is? So this is why I approached it this way. And often what you'll find with, I think, people that have really advanced critical reasoning skills is they will follow this type of thing. They won't necessarily try to answer the question right away. They'll say, okay, this is a great question, but before we answer that, we need to understand the foundations of the problem so that when we give the answer, it will make sense based on, like, the state of the world. So now that we understand hard science and soft science, it's probably really clear that mathematics is generally going to be considered hard science because mathematics is generally not subjective. Mathematics is generally objective. That 1 + 1 is 2. If I do it, if Taylor does it, if my dog does it, if the checkout clerk at the grocery store does it, we're all getting the same answer. Whereas if you ask, so if I say this, what's 1 + 1? And I ask 100 people, we would hope that the answer is 2. All right. Now, do another test. Ask them what their favorite color is. You're not going to get a universal answer. Why? Because it's not objective. That question is subjective. That's an example of soft science, is that you don't know because there is no, like, fixed objective truth here. Everybody can have their own favorite color. Does it make their favorite color wrong? No, it just means that it's decided by the subject. It's not decided by objective reality. And so along those lines, it should be clear that mathematics is generally considered hard science. So let's look at this and then we'll add a little bit more. So their answer is mathematics is generally considered a hard science, though some classify it as a formal science. Yes, this is actually a really important breakdown. Distinct from natural and social sciences. In the typical division, hard sciences are characterized by methodological rigor, logical structure, reliance on mathematical models, and the ability to produce precise, often universal, accepted results. Mathematics exemplifies these features. It is based on deduction, formal proof, abstract reasoning, high standards of demonstration, and internal consistency. Most sources that distinguish hard and soft sciences explicitly include mathematics among the hard sciences, alongside subjects such as physics and chemistry. In discussions of academic disciplines, some categorize further label mathematics as a hard pure discipline rather than like a hard natural, emphasizing the focus on fundamental research and discovery rather than direct application or empirical study. All right, so in summary, mathematics is classified as a hard science, or more precisely, a hard, pure formal science, again, as opposed to being something like natural science, due to its exactness, logical rigor, reliance on proofs, and highly structured methods. The distinction between hard and soft is a matter of, yeah. Sorry, the reason why I pause on this word is not that I don't know what this word is. This word is methodology. This word is used often in today's society far more than it probably should. Oftentimes when it's being used, what we really mean is method. In this case, it might be that we mean methodology. But so when I see this word, what happens in my brain is I think for a second, do they actually mean method here? Are they using it the wrong way? And so if you ever see me pause when I get to this word, it's that I'm trying to figure out if I should fix it to method or if it's actually correct. So in this particular case, it might be that it's correct. So we'll just continue. A distinction between hard and soft is a matter of methodology and the nature of the subject matter. And in this context, mathematics embodies the key traits of hardness. All right. Now, this is just what one AI system says. So I quickly just went to another AI, which is Google, and I asked Google, what do you think? Is it hard or soft science? And then Google says the same thing. It's generally considered hard science. While it differs from fields like physics and chemistry in its subject matter and methods, look at that, methods. This is what I'm saying. Methods, not methodology. Not methodologies, just methods. It relies on rigorous logic, proof-based reasoning, and quantifiable results, which are characteristic of hard sciences. Here's why math is classified as a hard science. Logical and deductive. Math is built on logical deduction and proof, meaning conclusions are derived from established axioms and theorems with certainty. Quantifiable and measurable. Mathematical concepts are often expressed through numbers and equations, allowing for precise calculations and measurements. Abstract and theoretical. Math explores abstract structures and relationships, often without direct physical representations, but these are abstract concepts that can be applied to solve real-world problems. Empirical validation, while not directly experimental in the same way as physics, mathematical theories are often tested and validated through their applications in other fields, including the natural and social sciences. While some argue that math's focus on abstract theory distinguishes it from empirical sciences, this is like the natural sciences, the rigor and precision of mathematical reasoning are central to the scientific method and are why it's considered a hard science. This is probably very much why I think about it like this, as a hard science. Perhaps a more precise way to talk about mathematics is that it is what Perplexity said, in that it is a formal science, in the sense that if hard science is about evaluating sort of the world objectively, mathematics is not necessarily. I mean, one could argue that it doesn't have the same type of analysis that you would do with biology or physics or things of that nature. It has that level of objectivity. And there are arguments that mathematics is one of the purest forms of science and that it is present in the natural world everywhere. And a concrete example of that is the golden ratio. The golden ratio is this essentially this mathematical equation that shows that for many objects that exist in the natural world, they take a shape that follows a very structured mathematical representation. You guys can, if you're not familiar with the golden ratio, you can Google it afterwards. But that would be a counterexample that mathematics is not just pure, that there is the presence of mathematics in the natural world that we've discovered. So, and supposedly the golden ratio stuff appears all over. I mean, it's like seashells do this. There's just a number of things that take this golden ratio form. So in the higher order bit, I think to bring this to close is I think that generally speaking, notice that even the language here, this is part of the reason why I teach the notion of weak claims. So even in something like mathematics, where one would be inclined to say, oh, it's a hard science, right? We see here it's saying generally, and it's not just Google. Perplexity did the same thing. It's generally. And I would argue that it also is generally, because I can see how one might argue that it's not, because it seems to not necessarily have a binding to the natural world, like physics or biology or chemistry have, or geology. But I also want to draw the distinction between what is commonly referred to as like the empirical sciences versus the social sciences. Social sciences are things like sociology, psychology, anthropology, blah, blah, blah. These empirical ones tend to be in the space of natural science. Okay. And so when we talk about hard science, we tend to be inclusive of the natural sciences, but it doesn't mean that it's just the natural science. So if someone were to say, would you consider mathematics a natural science? I might say no. I might say I'm not sure. I would consider it a hard science. And actually, I'm fairly compelled by the answer by perplexity that I would probably consider it more of a hard, pure formal science. And again, the reason for these words, just to be clear, so hard science, what is that? It's the objectivity and it's the repeatability. Pure, the pure part is it's abstract from the natural world. It's just it's pulled away, that you can reason about it without interacting with the natural world at all. And then the formal part is that it's often used as the basis. These are the tools that we build. It's a collection of tools that then we use for the evaluation of other hard sciences. So when we are measuring things in biology, chemistry, all those natural sciences, we'll use mathematics to do that evaluation. That's why people will often call it a formal science rather than a natural or social science. This part, I as close to 100% as I can, I agree with, is I think that this is probably the most precise definition that we've seen so far. And I also want to share, too, that what's interesting about this is this, I think, gets a little bit at the heart of weak claims, is that you're not saying it's a hard science. You're not saying it's a formal science, and you're not saying it's a pure science. You're saying that it's a fusion of all three of these things. I guess what they're trying to say here is pure formal is one thing. So in my mind, I think that you can actually have these as disjoint things. It can be three things, but in this case, it looks like they're defining it as two. Whatever the case is, that it's interesting that along with the weak claims, is they're trying to argue that, I think in some case it's blurred in that it's a hard science and it's a formal science together, and both of those things are a little bit nuanced. They're a little bit uncertain. The last thing I want to share is this relates back to what I was talking about on when we get to like advanced material for machine programming. Is I was talking about how when we get further along to the edge of science, there is no nomenclature for what we're going to discuss, that the words just don't exist. And this can be a little bit jarring for people that haven't like worked at the edge of science before. And it kind of makes sense that if you just sit in the world of where everything is known, then you would expect that everything is like always known. But then when you walk to like the edge of the planet or the edge of the known galaxy or the edge of science, suddenly there's just stuff and you're not quite sure. So this goes back to this notion of you have to sort of start to invent language that captures the essence of things, the concepts that are outside of the known space of science. So then you can start to reason about them more clearly, and then you actually iterate on the language. So, for example, even with the three pillars, I've mentioned many times that we didn't get exactly right. That's an example, is that even though we spent several years on that paper coming up with those three words, we missed a little. And so we probably are going to have to iteratively refine. But I think it's critically important to understand that that process of iterative refinement is the scientific method at work. Is that the idea that you would come out of the gate and be like, we've defined machine programming perfectly, this is the definition for forever? That's largely misguided. This is sort of like newbie research, newbie mad scientist 101 is, I think, more of the senior mad scientists. We all kind of know, well, we're not going to get this right, but we're going to try to get this as close to right. And then when people tell us we're wrong, we're going to iterate. Like, for example, even in this exploration, I would say that before this, I might have said mathematics is generally considered a hard science. Now, after doing this, I would say that I would actually probably say mathematics is generally considered a hard and formal science. I might or might not include this pure thing, just in the case that it could be misunderstood. Okay, now I realize that that exploration was wildly pedantic, and we literally just did an hour discussion of trying to understand what hard and soft science is, and then try to understand if mathematics is hard or soft science. And in some sense, I don't even know if we have a conclusion. We have mostly what I think is a belief that mathematics is generally hard science, maybe mostly it is, and that it has this pure formal aspect to it, which makes it the base of a lot of other scientific discoveries. But we haven't, I think, definitively said that it is this thing for sure. And part of that is, I think, that we don't really know. I mean, based on what we know right now, it generally feels like it's this, but we use the generally, again, using weak claims. Weak claims are absolutely your friend. The more advanced you get in your exploration of science, and the more rigorous you become, like, I think, as a scientist, the weaker your claims are likely to become. When I was like a newbie programmer, everything was a fact. This is this, this is this, is this. Now, as a 50-year-old man that has been teaching this stuff for quite some time, I see nuance almost everywhere. Literally, like even in this, right? It's just, it's incredible. So this goes back to our virtues: is prefer weak claims. Seriously, it's going to make your life so much easier. And it's not just, this is my view, it's not just that it'll likely make your life easier in terms of helping engage with other people. More than anything, I think it will help you improve your own ability to think critically. What I found personally, before I started really leaning into weak claims and I was using strong claims for most things, I had convinced myself of these non truths. I had decided that they're truths because I just said them as truths, even though they weren't. And it was jarring for me when people would say, well, that's not exactly right. Because in my head, I had said it that it was exactly right. And then other people were challenging me, except they were right. And then it took me a while to unlearn that behavior, right? To stop doing that. Because the truth is, I think it's much easier to communicate using strong claims. It often is also shorter, right? For example, it's fewer words to say mathematics is a hard science. Mathematics is a hard science. It's 5 words. How do we say it? The weakened form, the weak claim. Mathematics is generally considered a hard science. It's 7 words now. It takes more effort, generally speaking, just like that, to communicate in weak claims. But the beauty of the weak claims is they tend to actually be more precise rather than less precise because you allow it that level of granularity. Keep in mind, when you say something is definitively this or it is definitively not this, all it takes is one counterexample to prove you're wrong. So, for example, if I make the claim that all cars are blue, all you need to do is find one car that is not blue, and you've eviscerated my argument. Likewise, if I take the other argument and say that, put it in the negative, which is there are no cars that are blue, all you need to do is find one car that is blue, and you've destroyed my argument. Now, the inverse of those, which are weak claims, minor modification, and they are nearly impenetrable. A large majority of cars are blue. Now, let's just assume we live in a world where the large majority of cars are blue. That's going to be pretty tough to shoot down. Here's one that I think is probably more reasonable. The majority of human beings that are alive today are under 6'5" in their height. I think we probably all agree on that. But if I were to say all human beings are 6'5" or shorter, all you need to do is be like Shaq or whatever your favorite basketball player is, right? And so this is part of the beauty about weak claims is, one, they help sidestep random nonsensical debates that you're not trying to debate, you're just trying to get a general impression across. They will tend to lower, at least this is what I've seen, they tend to lower the need for people to disagree with you. And it also, more than anything, I think it actually expands your horizons. It helps you think more clearly. Admittedly, it's harder because the world isn't necessarily as binary as it was before. But the truth is, it wasn't binary to begin with. It's just that you thought it was binary. And so you just had like this misinterpretation of it. It's just actually lots of shades of gray in many cases. So anyway, I feel like this was a fun little rabbit hole we went down. Untranslatable metaphor. Hopefully this gets at your question and shed some light onto at least the way that I think about this and what these AIs think about this. I think the vote is still out, but generally speaking, I think this is the general scientific consensus that exists today. I think there likely will be evolution here. And I also agree with what Google was saying is that this is where did it say it? I thought it said it somewhere in here where they didn't quite like the breakdown of the hard and soft science anyway. Yeah, maybe. Yeah, I'm not sure. So anyway, I think we're ready to move on to topic 3. But before we do that, let's look at what Taylor's saying. Interesting about how you bound data collection in soft science and hard science. Yeah, it is. It's pretty crazy. And again, the only reason why I understand the soft science stuff is mostly my ex-wife just taught me tons of things. I was just like a sponge for her teaching me all this stuff. So I have tons more to learn, but I am interacting more and more with soft scientists these days for various things. So hopefully I'll continue to learn stuff, and as I learn any like major new gems, I'll make sure I try to share with everyone on GTT. Next comment. That's one lesson I'm grateful to have learned from you, Goju, regarding method versus methodology. Yeah, yeah. It's like one of those things where when I say hard science, I'm saying hard science because that's sort of like the only word I know that precisely captures the intuition of hard science. I'm not trying to sound fancy. I'm just trying to use the right word. And so similarly, when I'm talking about things that are methods, like Murley's machine learning is a machine learning method. It's not a methodology. A methodology is a collection of methods for this particular thing. So, for example, machine learning is I believe, a methodology. It is an entire grouping of many methods to do this specific thing. That's a methodology. It's a way of thinking. It's a way of approaching problems. So like rules-based heuristics is like a methodology, and there's many different ways to do rules. And then machine learning, I would argue, is a methodology because there's many different ways to do machine learning. But often what you see is people will, like, I think there's a confusion in that longer words make you smarter. And I don't buy into that at all. I actually believe the simpler the language to communicate precisely is the smarter approach. So use big words when you have to, but only when you have to. And so in many of the cases, what I find is the word method is perfectly acceptable. And the word methodology is actually wrong. And in fact, not only are we discussing it here, I have this as one of the things that I discuss at the university. And I find that initially the students will say, they'll be building a machine programming system, and then they'll say our methodology. And I'm like, no, it's your method. You didn't invent a collection of methods to do this thing. What you did is you built a system, and it has a method, and you're going to describe the method. So let's not try to sound super smart, because it actually, what I find truthfully is it does the opposite. Is when people are using these big words that are not the right words, and then there's simpler words that could be used. I think, at least for the super geniuses that I hang out with, I think there's a large preference for the simpler words. In fact, one of the super geniuses that, or the most accomplished scientist that I work with, researchers, all that, professor, is Maurice Herlihy. And Maurice is one of the people that taught me to use weak claims and use simple language. And in fact, I was just talking with him today, and his emails are like, it's so simple. It's like so easy to understand what he's saying because he generally strives to use the simplest language possible. So it's like, it's really illuminating, I think. When okay, maybe that's a little bit too, no, yeah, maybe that's a good one, of illuminating. I don't know that there's another word that might be shorter to capture that. There probably is, but it sheds some light on things when you think about people like Morris, who clearly his vocabulary is like 100x what mine is, yet he continues to use the simplest language possible, right? I think that that's fantastic.